In a previous video, we used nodal analysis using Kirchhoff's current law in order to find the potential difference in this spot right here, V naught. Now, Kirchhoff's current law states that the sum of all currents going in is equal to the sum of all currents going out. And by assuming that all currents are going out, this means that no current is going in, or the uh, the sum of currents going in is zero. Therefore, the sum of currents going out is also zero. So that's how we used Kirchhoff's current law in order to find the voltages in here using nodal analysis. Now we're going on to another method, which is a supernodal analysis. Now, nodal analysis will only work if there was no voltage sources in between nodes. There could be voltage sources, but there should be resistances in there. In this one, there's no resistor in here or in here, and there are two nodes here, and in between them is a lone voltage source with no resistors in between. So we call this one a supernode. All right. So and here's how we're going to uh, use supernodal analysis. First, let us assume that all currents are going out, just like nodal analysis. In this direction, in this direction, also in this direction. Not in this direction or this direction, since we will be taking care of that later. But let's just see how we're going to do this. So, supernodal analysis. I usually write SNDA to indicate I did the supernodal analysis at nodes A and B, a combined node, a supernode, if you will. So again, let's find the currents flowing through each part of the circuit. For the 10 ohm resistor, the only voltage source there is VA, or voltage source actually. It's not really a voltage source, but we can pretend it's a voltage source. So VA over 10 ohms gives us the current for this part of the track. And about this one, well, the only voltage source affecting it is again VA, so we can add that over 5 ohms. Now we will go through in VB here. Going down, there is a current source going flowing through it. So whatever resistors there are, we don't need to care about it because we already have a uh current source. So it's flowing away from the assumed current of VB, and it is 1 ampere. So we should subtract 1 ampere here. And for this one, the voltage source here goes up, so that contradicts this VB going away from it. So it's going in the opposite direction. So it should be subtract. So VB, we should add this, VB minus 2 volts over the total resistance in this circuit is 7 plus 3 or 10, but let's just put 7 plus 3 for completeness. And then due to nodal analysis, this is equal to 0. Now let's rearrange some things. 1/10 plus 1/5, that is 3/10 VA. Then VB over 10 is 1/10 VB. And then putting all the constants to the side, we get 1 plus 2 over 10, which is 1/5. So that would be 6 over 5. Yes. Okay. So what's the next constraint equation? Uh, this is equation 1. There are two variables in here, which means we need another equation. But how can we? We've run out of nodes here. Well, there is still the supernode. Inside the supernode, there should be an equation that we can do in order to differentiate VA from VB, right? So how do we get this exactly? Well, we assume now that, like nodal analysis, we assume, hold on, let me draw this. We assume that all currents are going that way and that way, opposite of each other. And then there is this 6 volt source here. So we can say VA, and then this is going that way, so it should be plus VB, and then minus sorry, hold on, we plus 6V, 6 volts. Then since VB is going the other way, we should subtract VB. And this is equal to 0. Another way to think about this, if you set VB as the positive And then VA and 6 volts are going the other way. So V minus VA minus 6 volts equals 0. And these are equal since if you multiply negative 1 to 1, you get the other, right? Another way to think about this is look at how, look at the pathway, I guess, or the flow of voltages in here. It's going this way since the 6 volt voltage source is going that way. And if you follow it, you can see that VA plus add 6 volts gives you VB. So VA here has some value, and then it passes through a voltage source going in the positive direction. So you add 6 volts to it, and then you get VB. So that's another way of looking at it. I will use VA minus VB equals negative 6. Uh, you can see that we can transpose both of these together in order to get the second equation, VA minus VB equals V6. You can use your favorite calculator program, but I will tell you the answer. VA is 1.5 volts. VB is 7.5 volts. So it's positive, so the ground, we assume that the ground was here, and it is indeed correct. The ground is there. So that's all for now. I will see you in next video.